Hello, how's it going? In this video, I'm going to have a look at parallel processing. The job of updating our world sort of decomposes into a number of substages. As you can see, originally we had all of this together as one thing, and also originally the job of writing the model matrices was handled by the app. But I just want to put it all here to make it a little clearer. It's always good just to verify what we're working with to start with. Okay, so this is the serial case, which is emulating the individual tasks individually. And we've got 100,000 cubes at about 20 something frames per second. But if we look over to the side, we can see that the CPU usage is quite small. We've got a lot of cores on this thing and we're only using one of them. So let's see if we can exploit anything here. I've actually in the starter code gone ahead and imported TaskFlow. TaskFlow is the third-party library that I use for all of my multi-threaded programming. It just works. It just makes things easy. It may not be the best way to do it, but it works. So what I'm going to do is I'm going to add in two things. I'm going to add in what's called an executor, and it will be the job of this executor to basically dispatch the work onto all the threads that we need. And then I'll have something called, strangely enough, this is going to be called a task flow, but I'm going to call it a task graph. So the idea is that I have a bunch of tasks and some tasks depend on other tasks, and the composition of all those things together as an abstract object is called a task graph. This is the thing that I throw over at my threads and I make them handle it. So what I'll do is just under my constructor, I'm going to make a new function called build task graph. And of course, I'll go and call that in the constructor. Just because I like a little bit of defensive programming, what I'll do is I will clear my task graph. Why not? And as we can see here, there's sort of 4 tasks. These 3 can each be performed individually. And then this task here is just a big for loop. And it turns out that multi-threaded programming has a concept of a parallel for, which is where we have a really big for loop, but then it gets dispatched on a bunch of different threads. So what I want to do is I want to do each of these 3 tasks, and I don't particularly care. They don't have anything to do with each other, but all 3 of these need to be done before this parallel for executes. So the first thing I'll do is I'll make those tasks. So I'll get my task graph and I'll in place. And I need to put on 3 functions, 3 lambdas basically. So for each of these, for my capture list, I'm going to capture the info I have about this instance of the class. For the argument, I'm going to take in nothing. And then for the update function, going to update pit, I said, pitch, and provide that delta time. So how am I getting around this issue of not being able to pass in arguments? Well, I've got access to this instance of the class, and up above, I've got an instance variable named dt. So what I'll do is when it comes time to update, I will update the class's dt variable, and then that will be read by the tasks in the task graph. So I'll just go ahead and put in the other tasks. This inPlace function takes in these function calls and sort of bakes them in there, and it creates something called a TF, a TaskFlow task object. So I'll keep that there, and now I'm going to make another one, which is, I'll call it write matrices. Now this will be a little bit different. Get my task graph, and I'll say for each index, need to put in a few things. I need to put in the beginning value of the index, the ending value, and I think these do need to be constants. I don't know, but I'll just put in 100,000, and then the step, which is 1, and then the task which will be performed for each of them. So again, I'll capture this. We do have an argument this time, which is the index I, and I'll call model matrix I. Currently, all these 4 tasks are swimming around somewhere. They're not structured at all. And we don't need structure for pitch, yaw, and roll. That's fine. They can do their own thing. But we do want all of those 3, pitch, yaw, and roll, to be completed before we go and look at the model matrices. So what I'll do is I'll take that write matrices task, and I'll say you are going to succeed all of these other tasks. Pitch, yaw, and roll. Isn't that simple? We've now generated a parallel task graph. So when it comes time to update, instead of doing all of this, we can just say, okay, take the executor, run our task graph, and then wait for that execution to finish. Okay, there's always a healthy amount of finger crossing that goes on with parallel programming, but here we can see we've got the same thing, our 100,000 cubes. We've gone up from 20 something frames per second to 110 frames per second. And more importantly, on the side, we can see that our CPU usage has gone way up, which is nice to see. I think maybe because OBS is running, I know I say this every video, but I was getting about 400 frames per second, up from 60 frames per second before. But yeah, so these past few videos have sort of been focusing on all the cool stuff that we can do just with our CPU, just crunching like a single list of numbers. But in data-oriented programming, the question which is one up from this is, okay, fine, but what do we do when we want to make a game that isn't just a million cubes? When we want to actually implement complex behavior? And this will be the focus of videos going forward in this series. Anyway, I talked too much. That'll be it for now. All the best. See you. Bye.